Good morning. It is 12:15 in Philadelphia. Welcome to Thermal Live 2016. It's day 2 and the final day here of Thermal Live. Welcome to all of our attendees around the world. I'm Graham Kilshaw with Electronics Cooling Magazine, and Electronics Cooling is the creator of Thermal Live. This presentation is the Fluid Network, optimizing hydraulic and thermal performance. And our speaker today is Chris Chapman from Avid Thermalloy. Good morning, Chris.
Good morning, Graham.
Chris will begin his presentation shortly. We're also joined in San Jose by the senior editor of Electronics Cooling Magazine, MP Divakar. As usual, good morning, MP. Bright and early for you.
Sure. Good morning, and again to our audience, good morning, good afternoon, or good evening. I know we have a global presence. It's a great day to get engaged and involved with the thermal management community, so I'm very glad to be part of this.
And MP will be joining us again later in the session as we get to the popular Q&A part of these presentations, which we'll talk about shortly. In fact, if this is your first webinar experience with Thermal Live, I want to just walk the attendees through a couple of the interesting features and tools on the platform. If you'd like to ask a question, you simply use the Q&A button at the bottom of your screens. You can enter those questions at any time during the presentation, and Chris and MP will do their very best to answer all of your questions as we get to the end. So as you think of your questions, send them in. Should you have any technical issues during the presentation, we'd refer you to the yellow tab on your screen, which lists many of the common issues that sometimes happen with webinars. That's the best way to solve them. One other great little feature of Thermal Live is that you can chat with other attendees that are live online today. Just use the group chat button at the bottom of your screen. And lastly, you'll see 2 links at the bottom of your screen. If you hover over them both, you'll see that the first one links you back to the Thermal Live site. You can still register for the remaining 3 or 4 presentations today. In fact, you can also register for the presentations that happened yesterday. One of the great features of digital media these days. You can watch the recordings from yesterday if you missed them. You can still sign up. And the second link at the bottom of your screen is a link to the Avid Thermalloy website, where you can find contact information, products, data sheets, etc. Now, before we begin, I see a couple of questions already. People asking, when will the slides be available? And we always get this question. The slides from Chris's presentation will be available in 24 to 48 hours from now. Since you're already registered, we will automatically send you an email when they're available. So there's no need to request them, no need to email us. You'll automatically receive an email in your inbox when they're ready. The video recording of the presentation today will be available within 1 to 2 hours, so pretty much right away after the presentation's over. If you want to watch it again or watch it again with colleagues, come back to the same link you used to register and you'll be able to watch that video recording within a couple of hours of today's presentation from Chris. And with that, I'm going to hand over the presentation to Chris Chapman, who's the Director of Product Management for Avid Thermalloy. Chris is joining us from Laconia, New Hampshire in New England. Chris, over to you.
Thank you very much, Graham, and welcome everybody. So I'm looking forward to presenting this paper on the Fluid Network, optimizing hydraulic and thermal performance. To go over the agenda for this presentation, I'm going to have a quick slide on introducing Avid Thermalloy. Then we're going to talk about how this applies to electronics cooling and really what the liquid cooling basis is that we're defining. And we'll walk through these bases in specific device interconnect, manifold and routing, and then controlled fluid delivery. And each of these areas will have main items that we'll talk more of. So Avid Thermalloy is one of the largest design, engineering, and manufacturing companies in the world focused solely on thermal management. So we have over 50 years in the industry. We have 9 engineering design centers located throughout the world. The design centers support our manufacturing and our products, and they also actually externally bill their design services to a lot of small customers and a lot of strategic customers. Part of the work that they do is really what I'm presenting here. So there's a lot of design innovation that we see at Avid. And below you see a lot of different products that we offer in liquid cooling, cold plate systems, heat exchangers, and then moving right into the traditional air cooling and the array of cooling solutions there. So to get into what I want to talk about, and one of the opportunities is that we see different markets requiring different thermal components. And where liquid cooling comes in, what we want to do is kind of genericize the electronics cooling for liquid. There's a lot of work in the datacom area around data centers that's very innovative, and it's growing leaps and bounds. But there's a lot of traditional liquid cooling, such as smart grid, motor drives, and medical. So I want to kind of focus this. You'll see some pictures, but I want to kind of keep it generic to any electronic enclosure. And under that basis, our definition is it's a network of interconnected components really organized to work together to reliably and effectively cool different complex electronic systems. And in this basis, we want to focus on the device and interconnect. This is the first layer of liquid cooling components and interconnects that interface directly with each of the electronic modules and trays. Then we move into the manifold and routing. This is the intermediate layer of components that route and deliver the fluid between all the other layers. And then we have the controlled fluid delivery basis. And this is the outer layer of the components where we have the motive power for the fluid, the heat exchangers, the facility basis, sensors, and controls. So in the device and interconnect basis, this is where we see the cold plate technologies. The cold plates make direct contact with the devices that we're cooling. It also can take heat away from the interconnect as well. So it's cold plates that go onto devices. It's cold plates that can connect with the circuitry, taking heat away from printed circuit boards, IGBT modules, any type of main heat generating component. And one part of this basis is fluid couplings. The ability to decouple the fluid from the device and interconnect is really required for serviceability. Data centers have a requirement for hot swappability as an example. When we look at cold plate technologies, there's a range of different cold plate technologies, and of course when we are interfacing different devices, the shapes change. But if we look at the main drivers of thermal performance, we look at the heat transfer coefficient. The heat transfer coefficient we've defined here is in watts per square centimeter degree C. The lowest performance is what we would call any sort of tube or high contact tube, where we're using a tube to move the fluid, and that is integrated into a plate, and we are taking the heat and conducting it through the plate and putting it right into the fluid as quickly as we can. The heat transfer coefficient for this type of technology is between 0.4 and 1 watts square centimeter degree C. Then we move into machine passages. These are assemblies that have intricate machined passages and then is joined with a cover using brazing or soldering or epoxy, depending on the pressures and the temperatures and the material compatibility. But this technology will improve the performance to about 0.5 to 2 in terms of watts square centimeter degree C. Then we can integrate internal fin structures. What you see in this picture is a lanced offset folded fin structure, and that increases the performance to 1 to 4 for the heat transfer coefficient. Then we can move into mesochannel. This is fins that are on the order of 0.2 millimeter thickness. That increases the performance substantially to 4 to 8 watts per square centimeter degree C. And then we can go into what we would call our microchannel. The microchannel is 0.06 millimeters feature size. And we can see there that we can see benefits upward to 12 to 20 watts per square centimeter degree C. So this is a range of different technologies that can be used with the representative performance. What you see here are CFD outputs of the cold plate. So using CFD tools, at Avid we have our own code called ACOOL, and what we do is we model the fluid flow through the cold plate and the fin structures, and we pay special attention of the port inlet and outlet locations, because what we have to do is not only look at the thermal performance, but we have to identify and model the hydraulic performance, because what I'm going to show you is the hydraulics are just as important as the thermals. When we're developing the full fluid network, we can't just assume that this is going to be fixed flow. The flow is very pressure dependent, and so this is where we're using a lot of the CFD tools to be able to predict the actual fluid flow that you see in the bottom right picture. So you can see the flow fields that are being distributed through this cold plate. Fluid couplings, there are many manufacturers, very reputable manufacturers of quick disconnect suppliers that we work with. And what we try to do is categorize them into small, medium, and large size fluid couplings. The small is a fluid flow where it's less than 2 liters per minute of flow, and the large is up to 50 to 70 liters per minute, and the medium is around 10 liters per minute. Of course, those numbers have some variation to it, but that's kind of how we categorize what we're seeing in terms of the fluid flow and what size quick disconnect that we're using. With increasing size, there's a flow coefficient, the CV, which is dependent upon the manufacturer of the actual fluid coupling, so that we see some variance. But typically it increases with increasing size, so that the flow rate has minimal pressure drop. And I've got on the next slide, you'll see how this is impacted. The typical equation for the flow coefficient is the flow rate times the square of the specific gravity and the pressure drop. And this is specific to these units. The CV here is English units. A KV, there's a similar equation, and that would be for SI units. So what we've done here at the bottom, you can see we've got a performance loop. So this is a loop of 2 mesochannel cold plates. They are in parallel with fluid couplings connected with tubing and fittings for this entire loop. So this is a loop that is essentially cooling 2 heat generation devices, either IGBTs, microprocessors, and it's moving out of this basis with 2 quick disconnects. The graph, if I look at the x-axis, is flow rate in liters per minute. The y-axis on the left is the thermal curve, and the only curve that's thermal is the black curve, and the other 3 colored codes are pressure drop, and that's on the secondary y-axis. And so what we're seeing here is that we have the thermal performance of the loop, and you can see that's a function of flow rate. And then what we have are several curves. The green curve is the pressure drop of just the loop without the quick disconnects. If we use small quick disconnects, we see the pressure curve in blue. And if we use medium-sized quick disconnects, we can see the pressure in the orange or brown curve. And this is important, as I'll show you, in selecting the right size quick disconnect, and understanding and managing the pressure drop. So in this case, if we're at 1.5 liters per minute going through this basis, and we're using small quick disconnects, we can see that the pressure drop is just under 4 psi. Whereas if we use the medium-sized QDs, we would be closer to 1 psi. The next basis is the manifold and routing. And what's important here is that typically the manifold will distribute the main flow into all of these device and interconnect basis. And the key is that we have to have parallel flow balancing. So distributing the flow evenly is critical to achieve parallel performance throughout the electronic system. So typically in a data center you have an array of server units. But what we see in power electronics is that you actually might have 2 or 3 different electronic or device interconnect bases that actually have much different flow rates. We still have to parallel the flow, but the parallel may not be in the same distribution. Whereas in data center, if there's 36 nodes, then the manifold's going to distribute that 36 into 36 smaller, evenly distributed flows into smaller cooling loops. We also see in the manifold and routing that there's the need for fluid control instrumentation. This is measuring the pressure drop of the fluid, the flow rate, the temperature. They're all paramount in making sure these systems are working properly. Just like working in air systems, we see a lot of control on acoustic, and we'll also see a lot of control on providing airflow based on the temperature that's required. What we see for fluid systems is that's still in its infancy, but the technology with control instruments does exist. It's just a matter of implementing them properly. So for parallel flow balancing, manifolds typically have ports which may or may not have mating quick disconnects to the device interconnect basis. We typically use large diameter tubing with correctly sized port fittings, which allows for uniform flow distribution with flexible hoses. And we also see blind mate quick disconnects for true hot swappable electronics. They require additional mechanical support through the backplane of the enclosure. For fluid control instrumentation, we see the use of valves. They're utilized to allow for fluid shutoff capabilities, and some can be used for control and modulating the flow to certain areas of the enclosure. Flow can be measured with either inline flow meters or even pressure transducers. If you know what a known volume is, you can make a calculation understanding what the pressure drop is under that known volume, and you can come up with the flow rate. We see filters are used to minimize particle sizes in the fluid. Leak detection has special wires that can be used to detect a leak and signal the system. We see leak detection used with valves for shutoff capability. And thermistors are used to measure the fluid temperature to make sure that the heat's being rejected properly to the liquid. So in our example, this is the pressure drop as a function of flow rate. Again, for the hydraulic performance, which takes into account the pressure drops of the manifold and the control instruments. So the orange curve on the bottom is the pressure drop of just the manifolding section. This is the distributing section. The gray curve is the control instrumentation that's used in this manifold. So if I add those together, I have my yellow pressure curve. That is the manifold routing basis. Now in this example, this manifold is feeding 36 branches to the device and interconnect basis. If I go back to the previous curve using the small quick disconnects, this is now my blue curve, and what I've done is I've taken the flow that we see here and divided by 36. That's essentially the flow that's going into each one of those device bases. And again, because this flow is parallel, that becomes the pressure drop that my system sees. So what we're looking at is the pressure drop of that device interconnect basis, in this case, based on the 36 branches, is actually greater than the manifold itself. The final basis we're going to talk about is the controlled fluid delivery basis. So this is where we use pumps and heat exchangers. This is what's driving the system. It's called a CDU, a controlled distribution unit for data centers. That's a common name for it, is a CDU. But we also see them, a chiller to some extent can be a controlled fluid delivery basis. But the key elements of this is the pump and the heat exchanger. The pump's critical because we have to drive the flow to overcome the overall pressure drop of the system. And the heat exchanger, in this case, it depends on the facility requirements. If the facility has liquid that we have to transfer the heat, we're using a liquid-to-liquid heat exchanger. Or if it's just room that we have to get the air, we have to remove the heat into the air of the room, then we're using an air-to-liquid heat exchanger. Also, we can use the heat exchanger to take heat that might be in the air somewhere in the rack, and we can use that in reverse to actually move the heat into the liquid. And we also can see that the heat exchanger can be a condenser if this system is a two-phase system with vapor and liquid. So what I'm going through in our example is a single-phase liquid cooling system, but it very well can be a two-phase system. And so the heat exchanger essentially becomes a condenser in that model. So talking about pumps, the pump reliability tends to be the overall system MTBF, mean time before failure, limitation in these systems. And as a result, we see many customers designing the system with an N+1 or N+2 requirement, where N refers to the number of pumps required to drive the fluid network. So this is a way to add redundancy into the system. The configuration of pumps in parallel and series really are important because we have to understand that, and that's a tool we can use to accommodate the hydraulic requirements of the system. In this curve, we can see that we have, again, pressure drop as a function of flow rate. We can see the black curve is actually the pump PQ characteristic. This is the single pump flow pressure drop curve. So this is the capability of this pump to be able to move the fluid at the pressure drop. If we put two of these pumps in series, then the corresponding performance will be the orange or brown curve. If we put two of these in parallel, the blue curve becomes the performance curve of these two pumps, and the green would be three of them in parallel. If we want to go with two pumps in series and two pumps in parallel, then the blue, the very top curve, becomes the pressure profile. And so you can see really quickly with a pump that you have a lot of confidence in, you have a lot of test data in, you can actually come up with configurations that can do quite a lot. On the heat exchanger side, on the air-to-liquid heat exchanger, you can see the picture shows traditional copper tube with aluminum fins. These are used to remove heat from the fluid in a closed loop where the cool air is heated and then dispersed into the air, and then that air is handled by the facility basis. Compact air-to-liquid heat exchangers can be used to remove heat from the airstream into the fluid for cases where direct liquid cooling at the device interconnect basis may not be cost effective. So if we have just a few cold plates on the large heat generating devices, but there's a lot of smaller components that are dissipating heat, we could use a heat exchanger in that airstream to capture the rest of that heat and then put that into the liquid. And there's times where that becomes cost effective. For the liquid-to-liquid heat exchangers, we typically use a plate fin approach where it's stainless steel plates, they're brazed together. This is used in the radiative floor heating industry, so it's fairly common. And so this, we use to exchange the heated fluid in our loop with the system using facility fluid based on the inlet and outlet temperature limits set by that facility. And as I mentioned, condensers could be used instead of the liquid-to-liquid heat exchanger when the flow is two-phase. So for the controlled fluid delivery basis, and again, looking at the same curve, the pressure drop as a function of fluid flow rate, we can see that in the yellow, that's our manifold routing basis we calculated before. The purple is the controlled fluid delivery basis with the pump, the heat exchanger, and some other ancillary components required to drive that system. And the blue is our device interconnect basis. And again, remember, we're not running 40 LPM through that small loop, but if we divide that 40 by 36, then we're running 1.1 or equivalent, much lower flow through there. But the pressure drop that we have is additive. And what you can see here is that we have our total system hydraulic impedance in the red curve. That is what we have to overcome. And so our solution curve is a liquid flow network solution. And here we also have, just like our very first slide, we do have thermal resistance on the left axis. We have pressure drop on the right y-axis, and our x-axis is flow rate again. The black curve is the thermal performance of the heat exchanger. In this case, this is the heat that's getting removed out of the system, and it's based on facility fluid out versus minus the in. So the outlet versus the inlet, that is the temperature difference that we're able to work with. And this removal is in kilowatts. So this is essentially based on a delta T and a power level. And I'll talk more about that in a second. We have the red curve, which is an increasing pressure flow curve. That's our total system hydraulic impedance. And what I've done is I've pulled the pump curves from the previous slide. And what I have is I have 2 pumps in parallel and 3 pumps in parallel. And we can see that where the red impedance curve intersects is our actual operating point. In this case, we're looking at a fluid flow of 67 liters per minute, which corresponds to a pressure drop of 14 psi. The thermal resistance in this case is 0.1 degrees C per kilowatt. So if our delta T allowed on the facility is 10 degrees C, we can remove 77 kilowatts. If it doubles to 20 C, well, we can double the power dissipation or the power rejection to 153 kilowatts. So this illustrates kind of the network solution that when we start looking at the entire system, that we can really start looking at optimizing. And then based on each of the bases that we're seeing, we can then optimize solutions within those areas. So some comments. Again, this doesn't answer everybody's question on liquid cooling, but it starts bringing to the forefront some of the key, I would say, engineering strategies of solving it. And so that's what we're really looking at is what are those liquid cooling design methods. We talked about CFD that's used at the cold plate level, calculating pressure drop. We use many different methods. MacroFlow is a common software package, and there's a lot of different ways of calculating the pressure drop. Independent of any specific type of market that's served by electronics equipment, a common engineering strategy can be used. So I've tried to keep this presentation kind of independent of any electronics market. And liquid cooling does offer tremendous gains in electronic packaging as it relates to performance and packaging density. This is where the industries such as Datacom, smart grid, drives definitely has leveraged the importance of liquid cooling. So I'd like to thank you all for sharing this with me, and we'll move this over to Graham and MP for questions.
Thanks, Chris. This is a very, very interesting area and of growing importance to a lot of engineers. So thank you for a very useful presentation as well. I can see some questions now starting to come into the chat field in our system. Attendees, if you have a question for Chris, if you have a question about liquid cooling generally, now would be the time for you to post those questions. Just simply use the Q&A button at the bottom of your screen and send those questions in right away. And with that, I'm going to hand over to MP Divakar, the senior editor for Electronics Cooling Magazine, who's going to field the Q&A set part of this presentation with Chris. I think we've got some very interesting questions lining up quite quickly. MP, over to you.
Thank you, Graham. Excellent presentation, Chris. I thoroughly enjoyed it. I'm going to lead off with the question from my side and then get to the audience right away after that. What are you seeing in the automotive sector, especially the electronics cooling of EVs, electric vehicles?
Well, we certainly see there's a tremendous amount of work on battery, maintaining the battery temperature, because that's going to, essentially provide best performance, longer life. But typically, the automotive industry, for the most part, has used liquid cooling a lot, and they can service it. What we see is that's pretty much a mature market in terms of liquid cooling. What we see, the biggest challenge is when people are introducing liquid into, I would say, more benign type environments that have never had liquid cooling. What do they do with the leak? There's a lot of fear that if there is a leak, this is going to bring a system down. One thing with the automotive, we just don't see it because, liquid's been used at the very forefront of automotive. You already have several different liquid loops. So by tapping some of that into cooling some of these new electronics in the automotive, definitely is challenging. We see that in a lot of the transmissions. We see it with new devices. But the key is that the controlled fluid delivery basis in automotive is pretty known and is the reliability is important, but you also bring the vehicle in for service. And so some of the things that we see in a system that's 7 years cannot leak actually doesn't quite have that requirement because you can actually service the automotive a little bit more. At a high level, that's kind of my answer to the question. Certainly, there are specific subsystems where you do need very long reliability because those are areas that you cannot service into. But we don't see the same sort of customer base having the same exact concerns. Automotive is definitely more mature when it comes to liquid.
Excellent. That makes a very good segue into the very first question, and that is from the audience, that is, by Ashutosh, and he was wanting to know what can be done to do leak detection. Do you need to have something?
Yeah, so leak detection is one of the things where we typically use leak wires that are, it's two wires that are coupled together, and it's electrically coupled if there is a leak. If there's a fluid that will actually close the circuit in the liquid. So these are traditional leak wire type approaches. And what we do is we'll put them at the bottom of many of these subsystems. If there is a leak detection and it's picked up by the system circuitry, if there is the use of a valve, we could trigger the valve to close and prevent any additional leaks from hurting the system. And so that's typically where we see leak detection being used. But really what we do in our systems is we do a very rigorous battery of leak testing prior to shipping. And we use pressure decay for integrity testing. We use helium leak testing. We use pressurization dwell and high temperature fatigue testing. Because again, most of our customers that we're supplying liquid systems to, we cannot have a leak. And so we have a very rigorous test battery that we can make sure that when we ship a product at time equals 0, that we're certain that it is not going to leak in the 7, 10, 20-year time frame that we're developing the product for. So leak detection is important for our customers, but what we find is there's really a leak intolerance that we have to design into our products.
Okay. We've had many more questions, so I'm going to do I would say, a random selection to get as many broader topics answered as possible. The next question comes from Steve. He's wanting to know that this is regarding the MTBF of pump as a concern that you brought up in the presentation. He's wanting to know if this is in the seals and bearings. What are the other failure points?
Well, the two failure points that we're very focused on, and that is the actual particle size that gets into the bearing. So we really control that. That's where filtering comes into play. So we filter to certain sizes that are quite small. And the second is the actual capacitors in the pump as well. So in the electronics of the pump, the worst thing that can happen is that if you've got a pump, and as I mentioned, N+1, you've got redundancy, you don't want to have a pump not working. You want to have the power load distributed throughout your pumps so that what we see is that all pumps are energized, because capacitor failure is also a big issue that we see in pumps. So those are the two areas that we really look at, and when we analyze pump construction and we look at MTBF, those are the two areas that we really focus on.
Okay. The next question comes from Stephen from Rocker. He's wanting to know what type of activity or work is being done with respect to shape optimization in liquid cooling devices.
Shape optimization?
Yeah.
Okay, so I'm assuming this could be cold plate shape. I'm not really sure.
I think that is, yes.
Okay, so a lot of it comes down to the heat load that we're seeing. So how is the heat coming into the cold plate? How is it distributed over the electronics, the silicon? And so that tells us where the fluid path needs to be, what the residency of the fluid is in order to remove the heat properly. Of course, mechanical attachment is absolutely critical as well. We've got to make sure we've got very good contact. What I didn't say here is that the thermal interface, when you're looking at liquid cooling, is actually very, very critical because of the small delta T's that we're seeing. So we have to have very good mounting forces, localized forces. We care about deformation over that force. And so I think what we look at for shape optimization is really balancing all of that with cost. So the CFD that I've shown is typically straight fins that go through with some sort of manifolding. And that's what we see to be really very optimal. When we start looking at long flow paths, using a folded fin structure with lanced offset folded fin actually will break up the turbulence and the boundary layers as a function of length. And so if we're going over 2 or 3 inches of length, of flow length, then using that sort of geometry makes a lot of sense. We also have a technology called Vortex Core, which is used for double-sided. So if we are putting thyristors on both sides of a cold plate, we have a technology that actually routes the fluid from one side back to the other side, and back and forth as it circumvents the entire cold plate from the inlet to the outlet. So I'm not sure if that answers the question, but that's the best I could do.
Okay. The next question in the data center application comes to us from Johanna, and the question is on the fluid to air exchanger. Can they be applied in the data center, applications to cool the racks with ambient air inside? I would imagine the ambient is basically the cold aisle air that's being blown into the cabinet.
Well, I think the majority of data centers today that have liquid cooling, the ultimate rejection is still into the air. That we don't see a lot of these facilities actually taking all the heat out directly with liquid. It makes sense to do it if you can take the heat out with liquid, because then you've got hot water that you could heat facilities with. But what we see is a lot of the liquid loops in data centers today are really for performance gains at the chip level, and they're still getting ultimately rejected into the air, where that facility is being removed by crack and cross systems. So today we certainly see that there's a lot of final heat exchange at the controlled delivery basis with an air to liquid heat exchanger. And we're starting to see the integration to liquid, but again, that's based on a facility to facility basis. So we're certainly poised to support both types of final heat exchanger exchange, and that's really, the fluid network that we're solving, that's typically fixed in the installation that we're working in.
Okay.
But yeah, there's a lot right now with air to liquid.
Yeah, I think I can recollect one of the visits I made in the AT&T data center. That seems like a liquid to liquid cooling or heat exchange, because they have some ponds outside the facility that is used for cooling the data center. So I'm just kind of making a comment. Let's go on to the next question, and this is by Tozer from Intel. He has a question on helium leak test. What is a reasonable criteria for liquid cooling plate loop?
So typically 10 to the -7 threshold to even 10 to the -8. What we typically do is we'll have a customer specification, and we go one exponent higher. So if the spec from the customer is 10 to the -6, we're doing 10 to the -7th. And that just is just having a level of buffer, because again, at that point of doing that level of threshold, we certainly want to mitigate any potential leak downstream, and that's just kind of the safety margin that we use. We will perform the helium leak test in both modes. We can flood the internal the wetted surfaces with helium, and we can sniff the outside, or we can go in reverse. We actually put a vacuum on the fluid channels in a helium environment, and we can detect if there's any helium that comes into the wetted channel.
Okay. Our next question is by Steve from Celestica, and he is wanting to know, I guess this is a product-related question, does Avid have a line of two-phase pumps suitable for electronics cooling?
No, we actually do not make pumps. We work with several strategic suppliers. We pretty much integrate the pumps into subsystems. So right now, we do make fans. We are not making a commercial pump today.
Another question, it's a follow-up by another Steve from Chill9, and that is, what fails besides the pump in a liquid cooling system?
Yeah, what fails besides the pump would be any of the joints, any of the fluid joints. Quick couplings could fail if there is any sort of particle size that gets introduced into the system. we can see that if people use the wrong material sets, we've seen corrosion. We've seen biological growth actually can foul and increase pressure drop and hurt performance. But typically the pump is the main candidate. And of course, any of the joints, the fittings, the fixtures, if they're improperly assembled and they're not tested properly, could leak over time, especially when these systems see excessive force, such as servicing, people are moving them. So again, that's kind of what we would see beyond the pump.
Okay. I suppose this will be the last question because we have a few left, but I think we'll do a follow-up for those. This last question comes from Ashutosh, and he's wanting to know, what is the risk level of corrosion in a fluid pipe network?
Yeah, that's very interesting. We've been doing liquid cooling for many, many years, and we don't see it in our products, but what we find is a lot of customers that haven't used our products, we've seen that there's been compatibility issues. The main area is obviously if you have a copper system, you certainly don't want aluminum. If you have an aluminum system, you don't want copper. And believe it or not, I've seen these systems mixed, and so it's crazy to see that. But the reality is that there's a lot of people that haven't experienced that. So that galvanic corrosion is probably the worst thing that can happen. So whenever we're looking at a copper system, we're keeping the material set brass, stainless, plastic, and we don't have an issue. And likewise, if we're looking at an aluminum-based system, especially if we're seeing DI water that's used with any insulating property, we make sure that there's no salts that are in the system at all. Typically, a lot of these systems are brazed. So in that case, we have to use a brazing process that doesn't have any flux. So those are kind of the two areas that I've really seen issues in the field. But typically, outside of that, we really don't see too much on the corrosion side.
Actually, the last answer somewhat answers one of the questions that I think Jean Paul from Schneider had. Deionized water and how does it impact the performance? And I think you just answered it. So we'll mark that as answered. Go ahead.
Yeah, I think the other thing with DI water is that, if it stays deionized, and this is why I'm saying we don't want to ionize it at all, it's not going to conduct electricity. We also see that when we're looking at the coolant itself, that there's a lot of work that's being done with different chemistries, with biofilm inhibitors, corrosion inhibitors, and that's there's a lot of technology and science in that area as well. So it certainly keeps us on our toes when we're looking at the fluid network, because all those things we have to look at and engineer solutions around.
Thank you. I think we have to wrap up with that. I know we ran a few minutes over. For the remaining questions, I think there was like a couple of questions left. We'll do a follow-up. For everyone's benefit, make sure you register for the remaining sessions. The slides and the video recording will be available. The video in a couple of hours. The slides will be available within 24 to 48 hours. For those of you who did not register yesterday, go ahead and register for those. You will get a link with the slide and video presentations. With that, we have to wrap up. Chris, thank you for a great session, and thanks to our audience. I see there is a high level of interest based on the Q&A in the products for liquid cooling and Avid in general. It's been a great day so far. Make sure those of you who are interested continue to sign up for the remaining sessions of Thermal Live. With that, I wish everyone a great day, and we'll see you next time. Thank you. Bye.